get started. Speaker today is Dominic from Yale, and he's going to give us, tell us about symmetry and topological order tensor networks, and says it's going to be pedagogical, so it's going to start with 1D, I guess.
Yeah. So Jung asked me to do some kind of pedagogical style, so I tried to go pretty slow and actually give a bit of an outline how you would get from thinking about tensor networks, things you can get other ways by thinking about physics in 1D, and then I'll move on to 2D, which is actually work I've done. So that reference there is kind of the last one in a series of papers. I did it in my PhD with Frank Verstraete, and that's why everything I worked on was tensor networks, because it's like his main focus, so he wants to do everything with tensor networks. But if you kind of are interested in any of this, then you can look in that paper and then kind of go back through all the other references. Cool. Okay. So yeah, I'll start by reviewing 1D and then move on to this 2D stuff. I may mention some fermionic versions of what happens when you have physical fermions in your systems, because everything's a little bit more complicated in those cases. But I'll mostly focus on spins. And because there's so few of you, feel free to derail me with questions. Also, thanks for coming, everyone who went through the rain this morning. So feel free to derail me with any specific questions you want to ask during it. Yeah, so the basic idea of why you might want to use tensor networks is they give you a very efficient description of, say, a wave function that's based on locality in space or space-time if you have some kind of auxiliary space-time. And the idea is that, the kind of coefficient of the wave function is some really high-rank tensor, but you want to use some principle of locality to break it up into a bunch of small tensors. So in this high-rank tensor, like we all know, the number of parameters is scaling exponentially with the number of degrees of freedom. It's kind of intractable to store it or manipulate it. But if you break it up into all these small tensors, then the number of degrees of freedom is just scaling with the number of, and you have sort of a constant amount of correlation between the neighboring degrees of freedom and no kind of long-range correlations, inbuilt at least, although they can emerge. Then at least storing this thing is efficient. And then in certain cases, you can actually find practical, kind of tractable algorithms to manipulate stuff, particularly in 1D, where it works super well. So speaking of that, I'll mostly focus on this, I'll fully focus on this case where we're thinking about ground states of gapped local Hamiltonians. And in that case, the ansatz is there is no auxiliary space-time, it's just you have your space, we'll probably have some lattice, we'll have spins, or maybe physical fermions, and then we'll have one tensor per site, and then we'll contract them with some correlation kind of indices in the tensors to the neighboring sites, and use that to build a big wave function. So I'll introduce those more specifically in a minute. But the idea is to use the locality we expect from exponential decay of correlations in these gap systems to represent things using this local structure. Okay. I think that's all I need to say. Oh yeah, and maybe, so if you don't care about tensor networks intrinsically, which I guess most people kind of in the US don't, you want them to be useful for some reason, and that's kind of what these guys in Europe who are mainly driving this want to. So in 1D it's been really useful, but it was just reinventing DMRG, if you like. In 2D so far it hasn't really beaten doing a cylinder DMRG, and that's kind of the goal, I guess. Really having some 2D numerics that will be better than just doing quasi 1D thing. The problem is the quasi 1D keeps getting better, so you have to. But anyway, that kind of goal of doing 2D numerics was kind of what drove us to do it. So I'm going to be using a blackboard and not talk about numerics. So you might be like, why? What is there to study? It's just some numerical method. So you just plug it in and then find a really good, way to optimize things. But what actually turns out is that in 2D, the things we're interested in studying, which would be symmetry-protected topological order or intrinsic topological order, if you're not careful, then the kind of generic class of wave functions you use actually will never have this order. So what we did in this sort of series of papers was just work out some nice classes that are general enough to describe things with these kind of topological orders. So we can do all symmetry-enriched topological order that is sort of non-chiral. Dealing with chiral things is a bit different. You can do it, but I won't talk about that in this talk. And then I'm also pretty much just going to focus on on-site unitary symmetries, but including, I think, lattice symmetries is not so hard. The most complicated thing is doing kind of time reversal, orientation reversal symmetries, but I'm not going to get into those details today. Okay, so let me just start from the start. and give you some notation. So maybe I should just ask, does everyone here already know the sort of tensor network notation, or should I start from there and just introduce
I think it's good to define
what I mean by the diagrams?
Yeah.
Okay, so
Briefly.
yeah, the idea of these diagrams is we just have some kind of graphical calculus that's basically like a planar algebra with, over C, and it's just some pictures that indicate some arrays of numbers, basically. So if I have a simple example, like some box that I label A, and it has one leg, then this leg will have labels like, we fix one to be I, and I is like equal to 1 up to some finite D. Everything will be like finite in this talk. And then if I fix this index, I'm just going to get this number, AI, which is a complex number. Okay. So if I kind of have two indices, I'm getting some matrix element. Yeah, let's see again. And then the only thing you really need to know to read the rest of the diagrams is that, yeah, if I kind of connect two tensors by a leg, it's summed over. There's some kind of like Penrose notation, I guess. It's kind of like Einstein notation. If you just have a leg that's not labeled, in the middle there, it's going to be summed over. So this would actually be some auxiliary index K, MIK, and KJ. Okay. And yeah, we're often kind of sloppy with associating the coefficients that would define a matrix with the actual matrix itself. So I might make that mistake, but if you get confused, then just ask me. Yeah, so maybe I can ask you a question. What if what would this diagram evaluate to? And then I close that. Does that make sense? Anyone want to guess what?
Trace
Yeah, exactly. It's just, will be trace of M as a matrix times M. And then just another comment that might come up later, might be a bit confusing, is when you do kind of Hermitian conjugation, really there's no kind of definition of input and output leg here. But if I kind of fix the left one to be input and the right one to be the output when I translate it into a matrix, then to do Hermitian conjugation, I just want to complex conjugate this, which I'll denote with a star, and like swap these legs. Okay. So just kind of swapping the legs is not going to be conjugation. You have to also complex conjugate it. Cool. So that is, let's say, associated to M dagger. All right. So with that, then you can define the class of states in 1D. So the idea is if we have some spins I1 up to IL, and let's think about them on like a periodic 1D chain. I can always write the wave function like just expand it in some basis. And let's just imagine each I just goes from 1 to D, some D-dimensional spin. But what I want is some class of states where this is kind of tractable. And so the structure of 1D kind of makes you think you should just have nearest neighbor correlations. And that is associated to a nice decomposition of this guy. So if you kind of just pose that, or look at a class of states where this is actually just a product of matrices, now it's very easy to at least compute the matrix element of any basis vector. Okay. So this would be like matrix product state ansatz. And let me just introduce some notation for that. So I'll call this, here I'm assuming all these A tensors, so they're 3 index tensors, and they're all the same for me. So let me say a little bit more about it. But I'll just say that given this state A and some length L, I define the MPS state for this tensor A on length L to be this. Okay. So the notation for this guy is you have this A tensor, and we have these auxiliary index, and then this physical index. The P runs from 1 to D, but these auxiliary ones we actually are kind of, it's a free parameter if we're doing a simulation. We can fix that to be some constant, so like maybe these I and J will run from 1 up to some bond dimension, chi, which we also keep to be constant. Otherwise, you could always find such a decomposition. Yeah, and then by sort of scaling this to be bigger, you're allowing more correlation, is the idea. And then, so the picture for this coefficient is just going to be, yeah, probably you've seen this before, a bunch of these guys in a chain, and then because I traced, you do periodic boundary conditions. So yeah, I'll kind of abuse notation and say like this is the state here. Yeah, okay. So yeah, so far it might also be bit like, why do you bother using this kind of notation? Because you can just write matrix equations. But once you go to higher dimensions, it's much harder to actually write equations that not using pictures. So that's kind of why we use the pictures, especially in this work. I think if you're just doing MPS, you don't really need to use them at all, because everything's like 1D. So you can just put the equation onto a line. Okay, so let's continue. So something that is a bit strange is we often talk about these things as ground states, but I haven't mentioned a Hamiltonian yet. But I should tell you that these things always come with a Hamiltonian, a local frustration-free Hamiltonian. And it turns out in 1D it's actually gap, but that's a bit tricky to show. And you might need a few technical assumptions from beyond what I've given. But in all cases, it's local and frustration-free, and it has this tensor network state as one of its ground states. And there's a condition on the tensors that I'll tell you later that tells you it's the unique ground state. So yeah, what is this Hamiltonian? It's like a sum of these local terms hi, and if we kind of look at a local patch around some site I, okay, then the way to construct this is you think of this as a map from like, so let's just kind of reshape this. So this is mapping from the bottom to the top, and the bottom will be c to the chi squared dimensional, and then the top will be like c to the d to some length L. So to make this Hamiltonian, you just need it to be kind of non-local enough. It's very local, but you just need it to pick the length scale such that d to the L is much bigger than chi squared, or a little bit bigger than chi squared. So you can see that's going to happen pretty quickly because, yeah, the scaling of this boundary is just fixed. It's always going to be chi squared, but as we make this length longer, this is going to grow like a length. And once that happens, the support, like sort of the image of this map, if you like, will be a very small subspace of the full space. And then what this H does is just project onto this image. So basically this H just goes along the chain and just says, like, does locally a patch look like the tensor network? So you can see that the tensor network will be in the ground state because it just checks, does it look like tensor network? Of course, the tensor network looks like tensor network locally. So does that make sense? This definition of the Hamiltonian.
So you didn't understand this diagram you drew. So you take a region of, is that like a subset of the entire chain?
Yeah, let's take just some piece, like from here to here, of length L, around some site.
And then what is the map you're doing?
And then we think of this map from these two virtual indices, which will have some bond dimension chi, to these physical spins. And we just kind of take enough physical spins so that the size of the bulk is much bigger than the boundary. And then this thing, like the image, can't be the full space because the domain was much smaller than the range. And so then all that the Hamiltonian does is just locally project onto the kind of the image. It just projects onto that subspace. Because it's like a linear subspace. And so the Hamiltonian is quite simple. Really, like intuitively, it's just looking at patches and checking the tensor network like. Yeah. So yeah, when we kind of are sloppy as well, and we talk about these states, about saying it's like a ground state or there's a Hamiltonian, but this is like the Hamiltonian we mean, basically. Okay. Yeah, so I should probably give some examples before I go on to see if it's making sense. Okay. Yeah, so if I define this tensor I to just be I is equal to 0 or 1, and this matrix element is just a half, then hopefully like the state that I would say, if I just kind of put this guy next to each other a bunch of times, does that diagram make sense? And does someone want to guess what state that is? Yeah, it's just the product state. So this is just like the plus state. And then, of course, it has a local parent Hamiltonian, which is just sum over I minus x on side I. Okay, slightly less trivial example. Then someone want to, tell me what that state is. If the local tensor is just a delta condition, and again, my degrees of freedom into 0 or 1. That should be GHC. Yeah, this one's just GHC state, so like 0 tensor n plus 1 tensor n. And you can see again, this has a local Hamiltonian. Although it's a different sort of phase to this one, at least if you have Z2 symmetry, because this one has a symmetry breaking and this one doesn't. So you start to see what these states can do. Okay, and then one final example. So let me just introduce another tensor that's like the Fourier transform matrix. So I and J are still Z2 spins. And then I want to do this one. Okay, so this one's still delta tensor. Then does someone know what this state is?
There's no physical indices.
These are the physical indices.
It's still delta.
Still delta? Not quite. So these ones are now allowed to be either 0 or 1 because this guy has is not 0, is not forcing the delta. So you actually have a sum over all variables, and there's some minus 1s going on depending on neighboring variables. So I'll give you a minute.
So no, it's minus.
Could give like a hint if you want.
Yeah.
So a hint is that if you think about the controlled Z gate, it's you can write it like this. Okay, with that tensor I introduced, and these are deltas again. So like this guy is actually just a bunch of control Z gates applied to this guy. Yeah, so does that ring any bells?
Cluster states.
Yeah, exactly. This is the cluster state, which is just equal to product of I, CZ, I plus 1 on this plus state. And it also has a local Hamiltonian. Okay, so now you see like, this is pretty much some simple examples already telling you all the things that MPS can do, at least for gapped ground states. We can have like this trivial states, of course, the symmetry breaking states, and also this sort of SPT state. Yep. So now,
is there a way to define such that it's just on like here you're doing like on the bond? Can you define cluster state just on like having an index like IJK like where?
oh, you mean like just group these guys into one tensor?
Oh, I see.
Then it'll be translation invariant. But yeah, maybe you don't like that it's kind of got this asymmetry. You can do some gauge transformation to make it more symmetric. And I'll talk about, so now we've kind of already seen from examples what they can do. And actually you can in general have a mix of like symmetry breaking and SPT. But the sort of nice thing is that for these MPS, the structure is kind of simple enough that you can really just look at the structure and prove that that's everything that can happen. And then some results I won't get to, but you can also basically prove that all 1D states, at least of gapped local Hamiltonians, arbitrary well approximated by MPS. And then these people from computer science background also prove that there's even like a provably efficient polynomial time algorithm to like go and find the ground state, which is like some weird, it's quite a weird algorithm that you wouldn't really do in practice, but in practice you use G and it works very well. So yeah, it's kind of a nice complete story there. But let me.
Some people have implemented that as a numerical algorithm, and it works quite well.
Oh yeah, okay, that's cool. I hadn't really followed the progress of that.
By Vidic and Motormich. Vidic was the computer science guy.
Yeah, it was Vidic and Vazirani and Landau, right, that had the original algorithm. No, that's cool. I should look into that.
So, if you want to approximate the ground state on a size, system size n to a fixed accuracy, you need to limit one dimension to scale of the system size, right?
Yeah, I think all the computer science results allow you to have polynomial one dimension.
Yeah. But from a point of view like analytical, like classifying phases, so it seems problematic.
Yeah, that's not ideal. It depends what you ask for. I think there's also some results about like if you have infinite size systems and you want some kind of to some fixed accuracy approximation of correlators or something, you can do with a finite one dimension and just increase it to get a better accuracy. But yeah, there's probably still really a gap there to proving, starting from like nothing except local Hamiltonians and then proving that everything's MPS, the constant one dimension, and then using the MPS results to get the structure of phases. Yeah, I think there's also some this stuff's all for like kind of finite bond dimension. And also you kind of want to take some limits of things going to infinity, which also haven't been dealt with, I think. Like not just the system size, but kind of letting bond dimension go to infinity. Because we always kind of deal with a fixed bond dimension, yeah, well, this is sort of a technicality, but I'll mention later. But then comparing things with different bond dimension is quite messy. So you want to kind of embed them all into one universal thing with like infinite bond dimension. Then the problem is like unless you restrict that, it can just describe everything, not just gap states. So yeah, there's some work left to do to, I think, finish the classification starting from just
bond
one.
dimension has to go to infinity for a finite system.
For these like computer science results, they like let the bond dimension grow polynomially with system size. But then in practice in say DMRG, you're doing like infinite systems and just fixing bond dimension to be a constant. And if you're interested in like some correlation functions, I think you can get that to be very good by just letting the bond dimension be some constant but big enough. Okay. Yeah. So now I'll take a different approach and just start from MPS and use the structure of MPS to find, say, basically these possibilities for the states. Okay. And let me give a reference for this. So I like this reference. But I should say all of these results are basically, or the ideas at least behind all of them, are from this much older paper by Fennis, Nachtigaller, and Vernov called like pure finitely correlated states. But it's easier to read in this paper. Okay, so the idea of an MPS is that its properties in terms of correlation functions are all determined by this one object called the transfer matrix. So if we want to look at something like, we have some MPS state, and we want to look at some correlation function, then if we turn this into a diagram, it's basically going to have O1 inserted somewhere. And let me be a bit sloppy. So A is going to be on the bottom, and A conjugated is going to be on the top. You can kind of check that A conjugated will give you the bra version of this ket state. Okay. And then you're going to have this tensor a bunch of times, the same one. And then you'll have this OL. And then let's imagine it's on kind of periodic boundary conditions, but sort of infinite. So that goes off and comes back around. There. Okay. Now, here, let's do 0 to L plus 1, so I can be lazy. We have this same tensor L times, and then basically on this outside part, we have the same tensor infinity times. So if L is becoming large, to work out what these correlation function properties are, we just really need to know the properties of this operator. So this thing I usually call the transfer operator. So E of A defined to be this thing. And then it has a nice connection to something that are almost quantum channels, and if you put one condition on, I think it becomes exactly quantum channels. So E of A acting on something, say acting on some operator rho, is this diagram. But you can just think of this diagram kind of just moving things around as something that looks just like a quantum channel. So if you write this as an equation, it's going to be just sum over the physical index, AI, rho, and then AI dagger. So like basically the MPS tensors are like these Krauss operators of this general evolution. So to see why that's kind of the picture of a general quantum evolution, if you have rho sitting here and you couple it to a bath or some environment thing, do some general unitary to mix everything up, and then trace out the environment degree of freedom, you can just basically block all this into one big tensor and then SVD it, and then find these Krauss operators. So that's kind of the general form of this. So then the nice thing is that if you're coming from quantum information and you have some idea about structure of the channels, then you can use that to basically classify what can happen with the MPS. Okay. And if we're interested in this kind of L being large, then we're interested in this limit of like E to the L, with L kind of going to infinity. And this will more or less, maybe a little bit sloppy, be given by, so for starters, I didn't mention normalization, but it's easy to normalize these states because to compute the norm is just to basically can just multiply a bunch of matrices. So let's assume we've already normalized this. If we've normalized this guy, then the largest eigenvalue is 1, because if the largest eigenvalue of this is kind of bigger than 1, then as you multiply this thing together, it's going to be blowing up. And if it's smaller than 1, it's going to be dying. So the largest eigenvalues of these guys have to sit on the unit circle. So I can kind of write sum over these lambdas in the unit circle, lambda times some, right eigenvector, depending on lambda, and some left eigenvector. And then plus, and here, this is pretty much just going to be like order the second eigenvalue. Let's call this thing delta, to the power of L. And delta is kind of strictly less than 1. So, yeah, if you take the limit of going to infinity, then the boundary conditions are just given to you by these left and right fixed points of this transfer operator. And you can see that if there's sort of only one of these, then this will have exponentially decaying correlations. But I'll come back to that in a minute.
So just to write it algebraically, the eigenvalues of which matrix it's...
So we're thinking about just the leading eigenvalues of this E as a matrix.
So let me understand that this diagram is this tensor notation, is it?
Yeah, I guess I'm using tensor notation for just these left and right eigenvectors, sorry.
So the transfer matrix itself is like one of those things, right? You sum of the physical index and you have these 4 those indices. And these eigenvectors are chi-squared dimensional.
Yeah, they're just some chi-squared dimensional vector you can think of, basically. So the thing we need to kind of understand is the structure of, well, what's coming from these guys. These are the important dominant. They dominate the behavior. Everything else is kind of dying off exponentially, is the idea. Okay.
This transfer matrix, what do we know about it? It's not a sort of measure, right?
Yeah, so maybe I should at this point put a condition on it. I think because of the way it's structured, it's like completely positive because it's written with Krauss operators. But to be really a quantum channel, you also want trace preserving. And that's something you can do without loss of generality. Well, let me do that now. I was going to do it later, but...
So I think maybe this is not the right way to write the number is it?
Which one?
In general, you have eigenvectors which are not orthogonal, and just write it in the form that you did, right?
Yeah, I'm not sure if this will make you happy, but you can bring this sort of thing without loss of generality into like a left canonical form, if you like. And the way to do that is if you just take these tensors and, well, let me say quickly, this is not super important, but you kind of QR decompose this, then you get something that's like a isometry part times this upper triangular part. Then you can push this upper triangular part into the next guy and continue this. And if this like converges basically, which is what people do numerically, then you're looking at tensors that have left eigenvalue 1 because this is an isometry. So basically, I have this Q guy here. The isometry condition is just that this equals this. Maybe I've like used that inadvertently. This only applies with summation. Yeah, I'm not really like using this just to get the idea, so this might be wrong. Yeah. But okay, let me make this condition now. Basically, without loss of generality, we want to use this form where we've brought the left eigenvectors to be. Well, yeah, I don't think this doesn't really make sense yet. Sorry, I need to do a bit more work on this structure before I can make this condition. But we could say the left identity is one of the left eigenvectors with eigenvalue 1. Okay. Cool. Okay. Oh, and yeah, I think I said that basically kind of classifying these transfer matrices is the same thing as classifying the MPS. this is only true up to a local change of basis, basically, because you can take this transfer matrix and singular value decompose across the middle to recover the tensors, but only up to some kind of isometry on the local Hilbert space. But if you're kind of classifying phases, you really don't care about that. It's going to be a basis change on each site individually on the chain. So as far as we care, basically E and tensor have the same information. Okay, so yeah, if you're thinking about these kind of operators, you can think about invariant subspaces and then bring one of the AIs into this form. So each of these matrices will be some like block acting in an invariant subspace up to some K. And then we might have something upper triangular. And then we have these off diagonal elements on this upper triangular piece. But on this lower triangular piece, because we're kind of finding invariant subspaces, there's not going to be some transition back to the previous subspace. So if we kind of have, I don't know, these invariant subspaces and so on, we can just bring this tensor into this form. And then the idea is, because so far we're only thinking about periodic boundary condition things, which is what we usually focus on, you can actually throw away this upper triangular guy and all these off-diagonal elements, and you'll have the same state. So this is equivalent on periodic boundary conditions. Sorry. To just these blocks. So we can think about these block diagonal and local tensor. And what this means for the actual state is that like A is going to be equal to the sum over this new index, A alpha. Okay. So you can see that some kind of symmetry breaking there, basically, assuming the blocks aren't the same. We're just getting a sum of different MPS states by going into this block form.
So how did you go into this dot form?
So I'm assuming that's periodic boundary conditions.
Yes.
And so when you go along the chain, let's say when you go along the chain, the algebra will act to either keep you in some invariant subspace or lift you to some other one containing it, but you can never kind of go back down. And so then when you trace, you kill all these off-diagonal things. And so you can just, it's a sort of a dumb reason, you can just throw them away and you have the same state. If you kind of do more complicated boundary conditions, so I don't know if you know about this W state, if you want to describe that, you need to have something that's definitely not like that couples the different blocks. But we're not really talking about those kind of things here. Okay.
Sorry, so what is the condition for this to work? That is
Periodic boundary conditions, and you close it with like
the W.
just trace, basically. You don't close it with some X matrix or something like that. Okay. Yep. And yeah, I think so. Without loss of generality, also each of these blocks, the channel coming from it will have only one eigenvalue, one eigenvalue, but it may have some other eigenvalues on the unit circle. So if we look at sort of this A1, it'll have a single eigenvector of eigenvalue 1, but then it may have some other eigenvalues on the unit circle. And you can use this kind of periodic decomposition of A1 now. So it has zeros along the diagonal. Oh yeah, and then another important property is that these other eigenvalues along the unit circle will come with some roots of unity. Okay, so now I know what to call this A11, and so on, A12, and then this one will be like A1. See. Okay, so now we have this kind of, and this is all zeros. This thing with blocks, but now they're sort of arranged just off diagonally, like kind of like a shift matrix. And this again introduces some symmetry breaking. So if you think about what this A1 state is going to be now, it'll kind of have first the A1 tensor, and then because it's moved up, it has to next apply A12, and so on. So it's actually going to be a sum of states. Some translates, and then the tensor for these MPSs you can think of as being A11, A12, and so on up to this A1C. And then you just have to translate these by 1 up to C. And so this is kind of like translation symmetry breaking, if you like, even though we weren't really assuming translation symmetry. I guess we did have it of the state. So again, yeah, if you have multiple blocks here, then you get this sum of MPS states. And each block basically kind of corresponds to one of the other eigenvalues, I think. So now but the nice thing you can do here is just kind of coarse grain some finite amount into one tensor again, and you reduce this kind of periodic thing back to the other kind of block structure. So if you coarse grain all these tensors into one, you'll have something that doesn't have this translation in symmetry breaking, just from the way we've coarse grained it, but it'll go back to having this block structure, but now each of the blocks won't have many eigenvalues, just by construction. So if you kind of coarse grain this, you're multiplying the eigenvalues together, and then if they're roots of unity, you do it enough so they all get mapped to 1. So then you have a bunch of 1 eigenvalues, and these all map to one block, but you don't have anything on the unit circle besides these 1. So then now we can kind of, without loss of generality, take this guy, which I'll call like a coarse-grained I, and it will be a single block. And it'll have its EA, sorry, question? With E having a single, one eigenvalue. And nothing else on the unit circle. Okay.
So just to go back, this translation symmetry breaking, despite having a single uniform tensor, you get translation symmetry breaking.
Yeah, it kind of, if you look at this guy, then each of these blocks has a single, so without making any more assumptions, each of these blocks has a single 1 eigenvalue, but it might have some more stuff around the unit circle at some complex roots of unity. And then each one of those eigenvalues will contribute basically a block. And so when you look at the tensor you get out of this, depending where you start, you just kind of pick up the same product, but starting from different points. Does that make sense? This is like a periodic decomposition of the Krauss operators, I think is what it's called. And then, but yeah, because they're at some complex roots of unity, there's some finite coarse graining you can do. And everything was finite, so it'll be some finite root of unity. You can just coarse grain it again to have no translation symmetry breaking. But now you have the additional thing you're sure of that there's nothing around the unit circle, because you kind of coarse grain in such a way that you mapped all them to 1. So you get back to this case, but now with the extra restriction that each one of these guys has a single, well, leads to an E with a single 1 eigenvalue. And then you take a single one of those. And that's where we wanted to arrive at, basically. So now this has this behavior, so E of L becoming large is basically dominated by this single thing. And I'll assume I'm in this form where like the left eigenvector is the identity. So this is just like a completely positive trace preserving channel now, which is really like a quantum operation, a general quantum operation. And then there's no summation, sorry, that's the whole point. This is just dominated by this behavior, so it's the left eigenvalue, and then it has some right leading eigenvalue eigenvector with eigenvalue 1. And I think you can also assume without loss of generality that this guy, if you only care about like sort of long range things, you can assume that this guy's full rank. Because if it wasn't full rank, you could basically throw away the states that it didn't have support on, and they wouldn't change any long range behavior. Because the idea is like when this is large, it's already projecting onto this subspace anyway. So yeah, and then let's say we're right, full rank. Sorry, and then this will be plus some gap to the next eigenvalue. So you can see here that you basically get exponential decay of correlations. I can show it more explicitly if it doesn't already make sense. But if you look at this correlation function of two operators, if you have L being large, up to this exponential correction, it will reduce into the single correlator. I mean, the single expectation value. Okay. Yeah, so this is sort of a nice condition to have. But there's also another condition people often mention. So I think this is, well, people call this different things, but sometimes they call it kind of a normal tensor or something like that. There's this other condition called injectivity, and then sometimes people call this injective, which can be a bit confusing. Injectivity is usually, or might also be defined by thinking about this map from the virtual to the physical indices. So let me define injectivity a different way and say why it's almost the same as this. So yeah, if we have this map again that we looked at before, from these virtual indices to the physical indices, this won't be full rank because the domain is much smaller than the range. And then generically, this should be injective. You can find like a left inverse. And that's the same thing as saying by accessing these degrees of freedom, you can like invert or work out what was happening up here, what the input was. So that's usually the way I would like to define injectivity. And then the subtlety is whether you say, does it become injective at some finite length, or is it already injective for a single tensor? And these are related by coarse graining. So if I just coarse grained all these into one big tensor, it would be injective as a single tensor. But this condition, so this also means, this implies that basically that AI of this coarse grained tensor generates a full matrix algebra, because if it didn't, then there would be other things commuting with it. And those things that commute with it, you could multiply rho by those things to get additional, like, 1 eigenvectors. So this thing has to generate a full matrix algebra. Because it does, then there'll be some length which you can go, and you can get, and because everything's finite, it's some constant length in the system size, where by accessing all these bonds, you can generate any matrix you want on the virtual bonds. That's the same thing as saying this is a full matrix algebra. And then if you can access any matrix element you want on the virtual bonds, that's the same thing as being able to invert this. So if you have this condition, then up to some finite coarse graining, it is actually injective. But there's a little subtlety whether if you don't coarse grain it, the individual tensor is not actually injective as a map from the virtual to physical. Like maybe the physical space is less than the virtual squared even. But when you coarse grain it some finite amount, it becomes injective. Yes. I think, let's say to be safe, I'll probably assume I've already done this coarse graining for the rest of the talk. So it's already really injective as a map from virtual to physical.
So roughly speaking, you're saying if I pick any virtual index there, with suitable choice of these physical indices, I can generate any matrix.
Yeah, so did it make sense what I said about this being a full matrix algebra? So if these Krauss operators didn't span a full matrix, or didn't generate a full matrix algebra, there'd be some stuff that commuted with them, with all of them. And then you could multiply rho by that to get more eigenvectors, and that would be like a contradiction. But because that generates a full matrix algebra, by just sort of fixing I1 up to IL, then the thing I produce up on these virtual bonds is just going to be this AI1 to AIL, which is some matrix element. But because it's full, I can, if I have enough bonds, everything's finite, so there'll be a sort of finite but coarse grained size where products will generate everything.
So you say generate everything
on this virtual, every matrix element on this virtual, every element of the matrix algebra on the virtual space.
So there's no matrix that will commute with those.
So there's nothing that will locally commute through. And this is like another way of saying the injectivity condition. Sorry, there won't be. So this equals this will imply x is like a phase times some constant. Okay. Times identity. Yeah. Yeah, and so if you have this, then you can kind of invert it, and the way to see it is that by just accessing these, you can really reconstruct anything there. Okay. Yeah, so at different times, different versions of the condition are useful. But yeah, this one of mapping from the like boundary to the bulk is the easier one to generalize to higher dimension, which I should probably get to. But let me first just finish the 1D story. Okay. Okay. So something I haven't mentioned really to this point is this sort of gauge freedom. And we fixed a little bit of the gauge freedom, but there's still a lot left. Because basically if we take this tensor, A, and we multiply by some invertible elements, x inverse, this will give the same state if we do periodic boundary conditions, right? Because each x inverse and the next x will just cancel with each other. So let's say this is equivalent to A. Okay. Oh yeah, and because of this condition we fixed where the left one eigen vector was the identity, this actually means that this x has to be unitary, because if you do like a non-unitary, you'll screw up this condition. So now we have this nice sort of gauge freedom, which is just a projective unitary. It's projective because if we have a phase, then we'll have the inverse phase and they'll cancel out. So it does nothing. It's a do-nothing transformation. And this, I think this action is like free because the unitaries are invertible, obviously. So yeah, this thing kind of has the structure of a fiber bundle. Maybe I'll do a little aside on this, because I kind of like this picture, but I don't know if it's really that useful for anything so far that I've found. But if you think about the space of kind of MPS tensors, and then the space of MPS states, let's say on periodic boundary conditions, with this translation invariant kind of structure, then you can find this map from here to here by just, let's say, for some L, you just construct the MPS state, length L. Okay, you just construct the MPS state from your tensor on that length. But then this is kind of a projection because a bunch of different gauge equivalent, at least, tensors go to the same thing. So actually over here, there's going to be like some whole ring of things that get mapped to one point over here. So this kind of has the structure of a fiber bundle. And there's even a paper about this, well, I don't have the reference here, that works out some geometry of this. And actually using these kind of ideas, there's ways to get nice algorithms that work on the tangent space of this space of states. So it's a really nice picture. But if we're thinking about the topology of it, you also have this action of the projective unitaries here. And it's free, and you can ask, like, is it a principal bundle? And then I think the most important other condition you want is to check whether it's transitive. So can I access everything in this fiber by just these gauge transformations? And then sort of the main result, well, one of the other main results of 1D MPS, I think Frank sometimes calls it like fundamental theorem of MPS, is that this is all the gauge freedom. So if you have two states that are equal, there will be some local transformation that relates them. And that means that this action is like transitive. And you think you need to check another condition, but I think it is actually a principal bundle. Yeah.
So this is after you made sure it's injective and so on.
Yeah, here I'm thinking about just these kind of injective tensors and also, well, to make the gauge structure nicer, I wanted this form, but you don't need this actually, that part. And then there probably is some other version that will be uglier when it's not injective. Because you do actually have a version that I'll come to later of this fundamental theorem when there's actually multiple blocks. Basically, all you need to do is if you have multiple blocks, you kind of have to first do a permutation to match things, and then you invoke this one per block. So it's not much more complicated.
So how do I see it? It should be a fiber bundle, and the fiber at each base point has to be isomorphic, right? But if there is a unitary U which just leaves this tensor invariant, then that would break that bundle, right?
Yeah, I just wanted to give the picture, but I can't actually explain it. I'm sorry. There definitely are some more conditions you need to check. I think they do actually work, and there's this paper by Frank and some people in his group that worked it out more carefully. Yeah, and then I think I want to skip the proof because I'm going to get to 2D stuff. But basically, to actually prove that this is transitive, you just require a clever use of Cauchy-Schwarz. That's all you need. And maybe to give the intuition, let me write the result. So basically, if you have this A state being equal to this B state. And it's kind of subtle. I think you actually only need it to be for like some fixed L but large enough. But usually we just kind of state it as for every L large enough. Or even in the infinite limit, I think is fine. Then implies there exists some x and theta such that, and if we're using this gauge, then it'll be unitary. Oh, let me call it V then. It's V unitary. Such that locally we have this equation. Okay. So I'm going to talk a bit about like finite group SVTs, but for finite group SVTs, if you're allowed to do some finite coarse graining, just phase doesn't really matter, so I'm also going to not include the phase. If you're thinking about like translation symmetry or having U1 feelings, that this phase is important, but I'm not going to cover that here. So you can also kind of forget the phase for the cases I'll talk about. Yeah, so how do you kind of find SVTs using this? It's kind of obvious because if you assume you have some symmetry, Gn, and this applied to A is going to be equal to A, then you can just invoke this. So there exists some G, and let's be sloppy about the phase, such that A with this UG applied is equal to VG A VG dagger. Okay. And you can already see that these VGs aren't only defined up to a phase, because if we have some phase here, it will cancel there. And then you can, I think there's probably seen this argument before, but basically because this UG is mapped to two of them, they only need to multiply up to a phase. So because G is like a rep, and this is going to give you some homomorphism, you need some condition like this, where omega is a phase. And this, of course, allows projective reps. And then because each VG is only defined up to some function to U1, we have like omega GH is similar to itself times something like this. Okay, and these two, so sorry, there's one thing else I skipped. If you look at these matrices, of course, they're associative, and that puts another condition on omega. And that constraint plus this relation just tells you that this equivalence class is in H upper 2 of G over U1. Like this constraint plus this equivalence is basically the definition, which is, if you're familiar with SVT phases in 1D, what you would expect to classify the spin SVT phases with like a on-site symmetry. Yeah. And maybe I should make a small mention of fermions in case people are interested in fermions at all. So for fermions, this whole story is a bit more complicated because everything's basically Z2 graded by fermion parity. So when you do this matrix algebra stuff, it's like simple, it's not simple normal matrix algebras, it's simple Z2 graded matrix algebras. So there's like an odd and an even type. And basically the odd type, I think, corresponds to the possibility of having a Majorana chain there. The even type ends up behaving very similar to the boson case. And then if you pick the if you pick the odd type, the symmetry stuff works quite differently too. If you pick the even type, then you get an extra piece of data here, which is pretty much just telling you, so I'll be a bit rough with this, but it's pretty much just telling you the grading of these, the fermion grading of these BGs. And then it actually twists this cohomology too. And that's actually just GU-when SVT. Okay, so that's sort of how you include fermions. And there are papers with more details about that.
So G is some group.
Sorry, I didn't introduce G. I'm probably thinking G is just some finite group. Yeah.
Each one of the first and second cohomologies.
Yeah. That's second cohomology, group cohomology. This is just like homomorphisms to Z2. Yeah, and again, if you really do it with fermions, this gets twisted, this equation, by some fermionic signs. But I didn't really mention much about that, so I'll just leave that as a comment. Yeah, so there's a few steps left to really prove that you actually, at least with these injective tensors, you're finding the classification of SVTs. But maybe I should just come back to the example. I showed you this cluster example, and you can see sort of nicely from these tensors how x on the left or x on the right pulls through. And I think I'll just tell you one equation you need, which is basically that up to normalization, this is just equal to z, Pauli x and Pauli z, I mean. So maybe from just seeing that, and then the properties of the delta tensor, can someone tell me what xl and xr get mapped to on the virtual level in this example?
What's XL?
So I mean x just acting on this left one and x acting on this right one. So if I have like a single x acting on the left, you can actually in this example just sort of just go through the computation and just move it through. So when you move it through this bubble, it becomes a z, and when you move x through this one, you have this equation. You also have an equation like this. Yeah, so I just thought that's like a fun little example where you can really see just immediately what they map to. So can you see what like this XL maps to?
Sorry, why is that this x conjugated by that circle is z?
It's basically the Fourier transform in this circle. So up to normalization, this is. You can check it as well, but it's just like Z2 Fourier transform.
That is not our Hadamard.
It is Hadamard up to a normalization, yeah.
But I thought that circle was this control z.
If you do this gate, which is a 2-qubit gate, it is control Z. But if you kind of apply this as a single qubit gate up to a normalization, it is Hadamard. Yeah. Well, anyway, it's pretty easy. You just kind of move this x, say to the x on the left. You move it through here, pick up an x there. This x becomes a z. The z can then hop through this guy, and then it becomes an x again on the right. And similarly for the x on the right, kill this guy. So this thing maps to x times x. Can you see how the x on the right would work? Well, you could probably guess from how the x on the left mapped, what it maps to. You don't want to guess? I can move on.
Symmetrical.
This one maps to z here because it will move to 2 x's and
Oh,
then
okay, right, never mind.
yeah. And so you can see if you look at a single edge, it's going to be like the Pauli rep of z2 times z2, which because it anti-commutes has this invariant that tells you it's in the non-trivial cohomology class. So that's like the way to see that this state, if you want from the MPS perspective, is in the non-trivial SPT phase of z2 times z2. Yep. So then let me just say a few comments about actually moving from this, just finding these projective reps to proving the classification. You need to sort of show that a continuous change can't change these, but they're discrete, so that's not very surprising. But you can kind of do it. You just look at, imagine a continuous change to like to the state, I think, and then you can pick a gauge such that that's going to induce a continuous change to the tensor because the state's like a polynomial in the tensors. And then once you have a continuous change of the tensor, you need to pick a gauge such that basically it induces a continuous change of these virtual matrices. And then once you're at the stage of having a continuous change of these virtual matrices, it basically can only induce a co-boundary. So there's a few little extra steps there, but it's not actually very surprising. And then I guess the other part that you need to show is that all things with the same cohomology class are equivalent. And that's a little bit more tricky just because you have to deal with comparing MPS that might have different bond dimensions. But maybe I can show you just a simple case, a simple example where, so if we have no symmetry, we want to show that all these states are in the same phase. And in that case, it's a bit easier. But the general idea is kind of similar. The idea is you want to bring all these states into sort of a canonical form via like a path of gapped Hamiltonians. So the way to do that is use the kind of polar decomposition, if that's the right word. So we'll have some Hermitian matrix H, and then some isometry omega. So you just polar decompose this. And then you can actually find like a path and show that it's gapped such that you can actually just delete the H. So now we just have an isometry. This omega is like an isometry. Yeah, so H will just have some real eigenvalues, and basically you just kind of slowly lift them all up to 1. And you can show the gap doesn't close along that path. And now if we also have this injectivity condition, let's just assume we have it for simplicity. This is basically just embedding up to a unitary here, which we don't care about. It's just embedding the virtual, or just acting as identity from the virtual indices to the physical index, because it's like an isometry. And then once you have this, the actual state you get, the MPS state you get, is just diamonds. But there's no symmetry protecting them, so that's just the same as the trivial state. So if you want, there's an extra last step where you kind of trivialize each pair of diamonds to just have like a plus state or a zero state on each, where each dimer was. So hopefully there's a rough idea. It can give you a picture of how you do it. When you have symmetry, these steps are more tricky. Like you have to preserve symmetry along all parts as well as preserving the gap. But that's the basic idea.
You just found a unitary circuit to disentangle the SPT. Is that what you're trying to do?
Yeah, so when we get to here, because there's no symmetry, you're allowed to apply any local unitary you like. So you can just map each diamond to a plus state. And then see it's really just decorrelated. Okay, let me mention a bit about 2D before my time's up.
Can I ask a quick
Yeah,
question?
sure.
So for like general symmetry, how do they come up with an A such that it's
Oh, so you want to do the question of how to construct an A in every class?
right?
There's some construction that's due to like Gu Wen, I think that's maybe Xie Chen as well on that paper. You can use like some topological quantum field theory basically. It's like if you think of the partition function, it has retriangulation invariance. Well, maybe I'm going too far. Basically, you just take the omega you want, pick some representative of it, and you can construct A directly from that. There's some recipe. It's something like this, if I can remember. You have these guys being labeled by group elements, and then you just apply this function here that's like omega of GH inverse H. And if you just take this tensor and stick it a bunch of times, and then the group action with which you're defining this with respect to is like just a left regular representation, then this will give you the right SPT. So, and also in the fermionic cases, there are recipes to, but they're based, if you want to, like, where do they come from? They're based on some ideas of state sum TQFTs. But there's always a recipe. Yeah.
Sorry, how do I interpret your diagram? You have the GH, what's the physical index there?
Oh yeah, so this, I mean, it's lovely. Here you have like these bonds that are just CG, like for some finite group G. So these live in like C of G.
Sorry, what do you mean C of G?
So just the vector space, it's like the span of basis states labeled by group elements.
Okay.
And the group elements, I just picked them to be orthogonal. That's my rule. Okay, and then this notation, I mean, yeah, without the phase, it would just be like the identity mapping from here to here. So the physical index is twice the dimension of each of the virtual one. But then
the physical index is like you have two
just
copies of the group elements.
exactly, it's just CG times CG. And then to make it non-trivial, all you need to do is just attach some phase to this. So instead of this just being this identity, when you have a function of G and H on these guys, and you just pick up some complex phase, which is going to be the cocycle or desire. And you can kind of check that you can move stuff through, unless I've sort of messed something up slightly, but that's the idea. And then you can check that it gives the right projective rep. And the same idea works in any dimension, which is kind of nice. So like you can make these states for all cohomology SPTs at least. And yeah, actually same idea works for topological states, but a bit generalized, which would give you like string net in 2D. Was there any other questions about 1D, or I'll just say a few things about 2D? Okay. So in 2D, the wave functions I'll be talking about are called projected-entangled pair states, but I don't really like that name, I don't know. Usually people just call them PEPS, so you just remember PEPS is a 2D wave function tensor network, that's fine. Projected-entangled pair state, if you like. Yeah, so this is going to be, let's assume we have like a square lattice for simplicity. It's going to be some tensor here, and now there's a bunch of indices. So let's label them like this. And then to find a state on a 2D square lattice, you just link this in the obvious way. Let's imagine this is kind of, well, either periodic or a patch of like an infinite 2D thing. Okay. Yep. So now the the state, which will be ground state of some local Hamiltonian, is just given by contracting this on the 2D square lattice. So should say a few things about the structure of these. So there's no full like nice theory starting from like nothing and kind of finding, starting from periodic boundary conditions, say, and then finding this decompositions. For example, we actually know that you can just basically take the 2D Ising classical partition function. You promote like each spin on each vertex to just being like a quantum degree of freedom, and then you can have correlation functions that are the same as the 2D classical Ising partition function, just by construction. And this tells you already there's going to be some that you can have a critical state here. Even though like by construction this has to satisfy the area law because the amount of entanglement crossing any cut is upper bounded by the number of these entangled, these correlation degrees of freedom. So it has to have area law, but you can have this kind of classical criticality there for sure. So these things don't have exponentially decaying correlations built in. So you can already tell they're a bit less well suited for describing ground states of gapped local Hamiltonians than 1D. Maybe you look at it as an advantage and think you can simulate some phase transitions. That would be an optimistic approach. But for classifying stuff, it's kind of annoying. So what you could do is just say, well, instead of proving things, I'll just put in some conditions to get nice classes of wave functions. And the most basic condition was just injectivity. So if you assume that, at some length scale, say we have some region R, we have all these bonds going into the region. We have this contraction inside the region, so let me call this like A inside the region, just contract all these tensors, and it maps from this boundary to this bulk. Then, so let's say AR, we can think of as a map from this like boundary Hilbert space, which will be scaling something like C chi size of the boundary to this bulk, which will be like C to the D to the size of the bulk. So it seems like quite a reasonable assumption, and I think if you pick generic A tensors that you do find injective things. Because this will be much smaller than this. So generically, it'll be full rank, and that means it will be like left invertible. But if you want to study this class of states, actually it turns out they're very boring for studying topological phases. So you can prove this implies a unique ground state on any manifold. And it's sort of known if you have unique ground state on the torus, it has to be be at least an invertible phase. So you can't have topologically non-trivial excitations. And then the other thing you actually get from this is that, similar to 1D, you can derive this, although it's a lot trickier, this pulling through condition, if you like. You can move any physical symmetry to the virtual level. But if you know anything about 2D SVTs, we usually classify them, or you can think about them by how they act on the boundary in some kind of anomalous way, which means when you restrict it to some subregion, it shouldn't be acting the same way that the group acts as like a linear rep of the group. It should be sort of non-associative in some way, or acting like a different group. So that's just to say, basically, having this boundary action tells you that the SVTs, this can't describe any non-trivial SVTs as well. So this one means no intrinsic topological order, and this one means basically no SVT.
How do you see the injective that has to be product and this is some unitary?
Yeah, that's not trivial. There's a paper by Perez Garcia. They do this. It's basically like what you end up doing is kind of like first you just treat it as like a 1D system and find that there's some big non-product operator acting on either side, and then you use a bunch of tricks to show the product operator actually breaks up. But I can't redo it in the board right now. These states for topological phases at least are very boring states to look at, and that's kind of the motivation of the whole project that linked to the where we ended up.
For PEPS, are we restricted to square lattices?
No, you can do any lattice. So you can even do any graph really. but let's say the things we will usually think about is some planar graph if we want to do 2D. And then often we actually have some kind of lattice structure. But you can do things that don't have like translation invariance or anything, just like a triangulation of a manifold or something like that. Yep, which is relevant for describing topological states. Okay. Yeah, so I was just going to mention that because Ying invited me, it doesn't seem like he's here, but so I'll tell a little bit. So maybe he can watch the video, so he'll be happy when he sees this. I should mention that I'll tell a little bit about our story, starting from this point. He has like a parallel story, and basically our result is we find some kind of generalized class that are not injective, and where there's sort of symmetry actions and symmetries are like matrix product operators. So basically the operator appearing here will be like an operator version of an MPS. But he has a different, so this is a nice general story. It lets you describe any like non-chiral symmetry-enriched topological order. He has a different way of doing it that is more practical, because when you have these MPOs, it makes everything much harder to deal with. Everything's kind of tied together. And he has this clever thing where they keep the kind of product structure, but just go to a bigger group, and that can also describe quite a lot of stuff, although seemingly not everything. So they can at least describe things where, well, if you have this SET and you gauge the symmetry part, what you're left with is a twisted Digraph-Witten theory. So there's kind of a parallel story to describe those things. But I'll tell you a little bit about our way of doing things in the last 10 minutes. So the basic idea following on from this paper, yes. So there was one work, well, two works actually, but this was the original work before we started that said, imagine if I'm not injective, but I have some left inverse, well, maybe right inverse the way I'm writing it. Oh, sorry, no. I want it to be left inverse. That was correct. So this will be some projector onto the sort of support space of this map from the virtual to the physical. And I don't want this to be the full space. But I also don't want this to be arbitrary. I need it to be kind of nicely uniform, or things are just impossible. And there was a previous work that said, imagine this as a projector onto an invariant subspace of like a product representation of a group. And that's what's in this paper. So it's a bit simpler than the really general case. And it allows you to describe quantum doubles without twisting. There was a follow-up to this that allowed you to describe this class of models called quantum doubles with twists. And like an SVT version of that would let you do cohomology SVTs. But this still could only do kind of like when this is a group, a generalized group projector. And then what we did was say, imagine this is just some MPO. And so if you have this big region, then if you look at this projector, it'll just look like this local thing on the boundary. So we kind of keep the locality, but not making everything totally decoupled. And this lets you do all string nets at least. So it kind of lets you access non-chiral topological phases.
So how do you define this right inverse?
I think it's just like the pseudo-inverse. This Penrose pseudo-inverse.
So this AR is restricting to this region, of course.
Yeah, so AR is from the boundary to these bulk physical spins, and then you bring this right inverse will act on the physical spins back to the boundary. So if it was kind of a generic map, it would be invertible because the physical spins is much bigger Hilbert space. But we want to look at this not generic class that can actually access topological order.
You think of a map as injective when projected onto the space, projected onto the space that's projected by the
Yeah, I think there's various things we prove, but then at some point we need some extra conditions because something can happen that this is kind of like a virtual symmetry, and if it's spontaneously broken or something, then yeah. So I think we want it that's injective on that subspace, yeah. Otherwise, yeah, you'd be looking at sort of the wrong MPO, right? You want the MPO that's sort of the maximal symmetry or something. Okay, and we also need some kind of homogeneity. But I should first say this is a projector, so let's call this whatever. This MPO squared is going to be equal to itself because it's just projecting onto the injectivity subspace by construction. So you can kind of go back to the 1D results and use this structure theorem to say the MPO is going to be equal to some blocks, because it also has like sort of just periodic boundary conditions. And if you actually really want to be careful, you do need some lattice decorations and things, but we'll maybe sloppy about them. There'll be some blocks, and then basically you have, well, let's call the box B. You have these individual MPOs that will be sort of injective individually. So yeah, it's sort of nice, this MPO should break up into these pieces. And then, because it's a projector, you have this equation that's like relating a bunch of products of MPOs to a bunch of single MPOs. And due to this sort of this structure theorem, there's a generalized version of this saying if two states are equal for all lengths that are injective, you can find the gauge relation. If two non-injective states are equal for all lengths, you kind of just have to match up the injective pieces on either side, and then you can invoke this gauge relation on the pieces. So you can actually kind of reorganize this and express each product of two guys here that will appear on this side. So if I have like OB prime as sum times a sort of fusion coefficient, if you like, which is just how many times that one occurs in the product. Yeah, so that's kind of coming from a generalized version of this gauge relation. And then you also have sort of the local version of this. For each one of these, there's actually going to be n, b, b prime, b double prime, different ways of locally kind of reducing this to this. So you have that if you have locally this b and this b double prime tensor, sorry, b prime tensor, there would exist some, let's call it x mu fusion tensors where mu equals 1 up to n b b prime, b double prime, such that this is going to hold. Okay, so you already have some kind of elements of an algebra and some local fusion of the algebra. And we technically need also that there is kind of an inverse to this. So we need the existence of its inverse such that if we had nu, oh, sorry, this is probably a bad thing. Yeah, if we had nu here, this is going to give you the same thing as this. So that's a slightly stronger condition, probably delta mu. So that is like one thing I'm still not quite satisfied with. We kind of use some general logic to get to this part, and then we need to have like a way to undo this fusion. Otherwise, we can't really get any further. But if you posit this, I think in some special cases when things are like groups, you can actually prove it, which was done more recently by Sirac's group. Then you can actually kind of find that what you really have is something like a fusion category. Okay. Okay, a few more minutes. So we now have these individual elements, which are like string types. We have this local fusion we can do with them. And then we have this degeneracy space, which is like the different choices of how we fuse them. And then if you think about having three of these guys, let's call them ABC now. And you fuse these in the correct order. You can fuse them one way via some E channel, or we could fuse them a different way. Then you can actually derive there's some F symbol relating these two different choices. Yes. Okay. And F you can just calculate from this. So this is, I think this kind of argument was first used by Xie in their 2D SPT paper, but it sort of generalizes to this more general case where you don't have a group, you have an algebra on a closed ring. Okay, cool. And I've just dropped the multiplicities here too, just for convenience. And then if you consider 4 of these strands and the different ways you would fuse them, you find the pentagon equation on F. So I probably won't go into that because it won't be too enlightening. But the upshot of it all is that basically from this MPO and then some structure and then one little assumption, we find that these operators behave like basically the elements of some fusion category. So we have some string diagrams, and these MPOs basically obey the string diagrams coming from a fusion category. And then if you want it to be like sort of unitary, you can put in a Hermitian assumption or have some kind of relation of different handedness. So if we had like a left-handed and a right-handed, they should be related in some way, which gives you a notion of inverse, and then that you can use that to derive unitarity. So the sort of upshot of that is, let's say, these MPO algebras, in some sense equivalent to unitary fusion categories. And if that doesn't mean anything, but if you know much about 2D topological phases, the Levin-Wen model is based on this input of a unitary fusion category. And I think the way we do it is kind of actually just a different way of enforcing. So I should say one extra thing. So yeah, I made this assumption about this being kind of homogeneous, but it actually turns out that that is equivalent to this local condition that this same MPO, or any string of this MPO, B, can actually just be moved through locally. So this seemed like a horrible condition, actually, if you think about it, because it's like saying you have to have that and the same thing appearing at all length scales. It's a bad thing you can't check locally. But actually it implies this, and this implies vice versa. That you have this condition for a single tensor, and then also that these things can move freely through the lattice. And once you have that, then basically your tensor network wave function can have these string symmetries inside it, and they don't really do anything. They're just a virtual symmetry. It's like a gauge symmetry. And this thing usually would call like local relations in the fusion category language is just imposed by these, or is enforced by these like equations you get by symmetries of the tensor. So you can actually forget basically about the whole tensor network. Say we had it on some torus. You can forget, if you want to think about topological properties, about the actual underlying tensors as long as it's fine-grained enough. And just think about these pictures of string, MPO strings on top of it. And yeah, this is like I was saying, if you know anything about Levin-Wen models, this Hamiltonian is meant to induce this thing that's called like diagrams mod local relations. So it has some like vertex term that constrains to consistent diagrams, and then some Plaquette terms that fluctuates them or enforces local relations. But here we're doing it sort of a slightly different way, where the diagrams will just be some symmetry and the local relations will be like an equality. And so this lets you do quite a lot, basically find all the topological structure of these things. So let me just give you one example and then I'll stop. You can find the ground states by just thinking about basically the minimal, well, you can span the ground space by thinking about the minimal states you can write on a torus. So if we had these symmetries, then we could just use the fusion to bring them into a form like this. That will be A, that will be B, and some C. And then if you look at the span of these things, that will equal the ground space. Yeah, and if I had more time, I would tell you about how you find minimally entangled states and excitations. And I was meant to mention SETs, but that's also kind of really nice slight generalization where all you need is on this structure is an extra grading. So on this algebra of MPOs, you need that there's some homomorphism to like a group, basically. And then each string will have some group type. So the G. And this equation is only true up to the symmetry. So it's kind of generalizing this pulling through of the physical symmetry to allow it to create like a string. And then actually really similar logic holds, except in these pictures, if this was some BG string, you'd have to have like G action on the domain inside there for it to be kind of a symmetry. Otherwise it would be like a defect. And then if you apply the logic of these diagrams, modulo local relations, you get like not only the ground states, but also the twisted sectors. And you can find all the defects and actually recover like the emergent excitations by thinking about sort of ground states basically on pairs of pants and so on. Yeah. So I think I should probably stop there. I don't take too much of your time. But yeah, thanks for listening.
So that there is like one of the ground states?
This will be in the ground space, yeah. Well, it actually depends. If you have like a abelian model, then your like ground space will be projected onto some operator that's acting here. And so that's why I didn't get up to talking about the minimally entangled states, but really to find like more like a basis for the ground states, you should actually form some special states out of combinations of these.
I guess my question was say like on the torus, how do we get the other ground states for topological order?
Oh, so this should at least span the ground space, I think. Basically, this is, oh yeah, so I think for the tensor network, I got a bit confused. This is actually ground state, because the idea is the Hamiltonian, it just looks somewhere and says, does it look like tensor network? So it's fine everywhere except when it crosses here, right? But these are symmetries, so actually I can just do this. And so it actually still looks like the ground state. Does that make sense? So it's in the ground space. And then you can actually kind of, by some counting, basically show that you find all of them. But if you want to see like a more careful proof, in the first paper we wrote about this stuff, without using much about fusion categories, we show that these things we find span the ground space.
Oh, but
If you have
so
this in the
this gives you
injectivity.
all.
Yeah, this will span all of them, the whole ground space.
I was just wondering, suppose I have this PEPS and I calculate my wave function, that would just give me one of the ground states.
Yeah, so if you say take the normal PEPS, you would just have the one where these are all trivial. Yeah. And that would just be some ground state, yeah.
I was just wondering from then, suppose I have that, how do we get the other?
Oh, how do you like re-expand that back into the basis of the other guys or something? I don't really understand.
Like I thought this gives you a ground state of a topological order,
Yeah, it does.
and then how do I get the other
Oh,
ground states?
you insert these like MPO twists basically. So if A and B and C are all trivial, you'd have the sort of normal ground state you'd write down. But then basically when you want to close the boundary conditions, imagine I had my tensor network inside these regions. So this is just a disk I'm drawing, but I'm putting the disk on the torus, and I want to like join this tensor network up to close it. Then the usual way of closing it would just be contract across here, right? And I'd get the usual ground state. But now what I do is when I contract across here, I just insert a twist of the MPO, and then I need to resolve this point. But that's the idea. It's basically when you contract it, you just put in this twisted boundary condition.
Just to make sure I understand this, OB, the labels B, do you run over the set of anyons?
Yeah, so if it's, these will run over like the string types if you like, and so the MPO labels are like the string types in a level-n model. And then, yeah, if you kind of construct this, category, like braided category of excitations, they'll be like the center of this. So in the case that like this was already braided, they would be just labeled by, the emergent excitations would be labeled by pairs of these Bs. But yeah, in that case, they would label like an anion in one chiral half, I guess, if it already had a braiding. But then you can do more general things where it's not splitting into two chiral halves. But yeah, it sort of turns out the upshot is the topological orders you can describe. You can go away from like fixed points, but they're all in the same phase as these models that have commuting projector Hamiltonians. Yeah. Okay.
Any more questions? Dominic again.
Oh yeah, so I was asking Thorngren already about this. Did you think about like 2D Lies models for these defect networks? So
I was just thinking about some random thing the other day. Yeah, there should be. Just check. On the center has disappeared. So, sure. Dominic, could you switch over to the video? Oh, yes. Okay. I can work do it. Not that I know. Yeah. Stop. Stop.